In this video, I want to give a simple overview without doing all the math of the simple harmonic oscillator. So I want to focus more on the physics, but of course we have a lot of math here, so I will have to explain what we are doing, what we are actually doing. And I want to explain the quantum harmonic oscillator by means of the path integral. So that's the physical intuition that I want to go through in this video. So I want to explain the simple harmonic oscillator, but I want to do so by using the path integral formulation of quantum mechanics. So the starting point is the Lagrangian. The Lagrangian, since we are talking about a classical theory, so it's a non-relativistic theory in this case, we have the kinetic energy, which is 1/2 the mass of the oscillator times the velocity squared, x dot squared. That's quite simple. And then we subtract the potential energy of the oscillator. The potential energy can be written as 1/2 the mass of the oscillator. Then we have the angular frequency of the oscillator squared times the displacement with respect to the rest position of the oscillator squared. Now, what Wikipedia writes here, and by the way, we are on the following page, so we are on the path integral formulation page of Wikipedia. You can just type path integral formulation and go to the Wikipedia page, and you should be redirected here. And you have this section on the simple harmonic oscillator. Now, once you write down the Lagrangian, of course, you can also write down the equations of motion, and in principle you can solve them, but the solution is not complicated. I mean, the classical solution. So the classical solution, one way to write it is this one that I'm trying to highlight. You can see that basically we have a sum of two sinusoids, so it can be written in this fashion. In principle, this could also be written as just one sinusoid, but in this case, you can see that if we set, for example, t equal to ti, this expression will give you xc of ti equal to xi. So this subscript c stands for the classical trajectory. Xc of t is the classical trajectory. So at first we are considering just the classical trajectory, but later we will be focused on the perturbation, which is expressed by means of this delta x of t of the classical trajectory when we consider the quantum behavior. And then this perturbation will also cause a perturbation of the action with respect to the classical action. So we write down the classical trajectory by avoiding a description of the quantum aspects, and we can see that this displacement is equal to xi when t is equal to ti and is equal to xf when t is equal to tf. It's quite easy to see. And then you can also put this expression xc of t inside the Lagrangian. So you can consider this function. You can take this derivative x dot and you can square it to find the kinetic energy and also the potential energy. And you can carry out this integration that you can see here. When we integrate from ti to tf, we can do that kind of integral. We can perform the integral, and here you get the classical action. Quite simple. Then we have something trickier because we have to add the perturbation delta x of t, and in this case I want to add some more details with respect to Wikipedia because it might not be too obvious that the perturbed action can be written in this form. So in this case I want to tell you more about it. So at first we consider this perturbation delta x of t, and I want to define, so I want to stick to the Wikipedia page, so I want to write down an expression that Wikipedia takes for granted without writing it down. So we have the small perturbation of the trajectory, which we call delta x. This is a function of time, if you want, but I will just write it delta x for simplicity. Well, we can write down a series expansion of this, so we can write a summation over n from 1 to infinity. We have some coefficients that in principle we have to calculate. We don't know these coefficients. And then we have the sign, for example, of n pi t minus ti divided by Tf minus Ti. So we write down delta x as an expansion. And why did they choose this kind of expansion? Well, one easy way to see that is that delta x evaluated at t equal to Ti should be equal to 0, and also delta x of Tf should be equal to 0. Why is that? Well, because when we perturb the trajectory, the classical trajectory, we keep the endpoints fixed, and basically we are considering the curves that are something like this. So we keep the endpoints fixed, and this is what you do basically when you consider also the path integral. You consider a starting point and an endpoint, and then you consider the possibilities that you can have. So you have an infinite amount of possible paths, each of which is associated with a certain probability or probability amplitude, whose magnitude squared will give you probability, but whatever, you have a certain range of most likely paths that the particle can choose, quote unquote particle and quote unquote choose. So we choose a function like this, we expand it, and we can see that we can write down the signs here, because if you evaluate this sign at t equal to Ti, you get 0, so you have the sign of 0, which is 0, but also when you evaluate the sign at t equal to Tf, you will get 0, because you have the sign of n pi times 1, because you have Tf minus Ti divided by Tf minus Ti, which will give you 1, so you have the sign of n pi, but that's 0, right? So once you write this expression, you can also evaluate at this point the change in the action. So this delta S is a perturbation of the action due to the perturbation of the trajectory. So this can be written as an integral from Ti to Tf of a perturbation of the Lagrangian multiplied by dt, and this can be written in turn as integral from Ti to Tf. Then you have 1/2 the mass of the oscillator, or I can call it particle if you want. You have delta x dot squared, so basically is the derivative of this expression. And then you have minus 1/2 the mass of the oscillator, omega squared delta x squared, and then dt. So let me do one more step here. I can integrate by parts this first term and rewrite it like this. So I can rewrite the action as minus. I can factor out this minus here, but I will also get another minus from the integration by parts of this term. So I get integral from Ti to Tf, 1/2 m. You have the second derivative of delta x, and this multiplies delta x, right? Because this term can also be written as d over dt of delta x times d over dt of delta x. So once you integrate by parts, one of these two derivatives will act on the other term, and you will get a minus. So for example, you get something like this minus, this will become d squared dt squared, and then you will get rid of this derivative operator on the second term. So you can write the term like this, because you can also show that you have a boundary term that vanishes when you integrate by parts. And it is due to this choice. So we have chosen delta x such that it is 0 at the boundary. So due to this property of delta x, well, it's easy to see that the action, once you integrate by parts, can be written like this. So you have this term plus 1/2 m omega squared delta x squared delta t. So now I don't want to do all the calculations in this video, because I prefer the intuitive physical understanding behind these mathematical calculations. Now the task is quite simple. We have to replace delta x with its expression that we have imposed, this expression here. Here you also have to calculate the second derivative, which is not very complicated. It's actually very simple, because here you have to treat this series as a sum of, it's an infinite sum, but it's still a sum of sinusoids, and you can take the derivatives of each term, and then you can put the summation outside the integral, and you can perform the integration. And what you get once you do this is what Wikipedia writes here. So it's exactly this expression here. You can carry out the integrals. You have integrals of sinusoids which can be performed. And by the way, those sinusoids are quote-unquote orthogonal. They are orthogonal functions. And you get something like this. At this point, Wikipedia introduces the propagator. So in order to consider the path integral formulation, you have to write down a propagator, which is indeed exactly the path integral. So the propagator that Wikipedia writes there is something like this. It's called k. Okay, we define it as k, which is the propagator, xftf, which are, so this is the endpoint. This is a spatial variable. Then we have a time variable, tf, and then we have also an initial time, ti, and an initial point, xi, like this. And this is proportional, so this proportionality is due to some normalization factor. You have an integral of some measure. You have a measure, and in particular, if we are in the frequency domain, the variables of integration will become these coefficients, the a sub n's. So you have something like dA1, dA2, dot, 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 dAn, and then you have the exponential of e to the I sc plus delta s divided by h bar. Now, at this point, Wikipedia writes down the expression for the propagator, so you have a product of integrals here because you have an exponential of e to the I sc, which is factored out of these integrals. It's written here, e to the I sc over h bar, and then if you write down the expression of e to the I delta s over h bar, since you have a summation of sinusoids, and in particular the expression that we have is this summation here once you perform the integrations, the exponential of a sum is equal to the product of the single exponentials, right? So you have a product of exponentials there, which are Gaussian integrals to be performed. They are integrals of the following kind. So I have also another Wikipedia page here readily available because I want to show you that, for example, an integral of an exponential from minus infinity to plus infinity of something like this. You have I, which multiplies a constant a, and then you have the variable squared. And in our case, you can set j equal to 0 because you don't have such term. So this term here, exp of minus I j squared over 2a will become equal to 1 because j is equal to 0. So you have an integral that can be calculated, right? And you have a product of those integrals. And the expression can be written in the following fashion. So I don't want to do the calculations here. As I said, there is also a normalization factor, which is not really important for what we are interested in this lecture, but never mind. So Wikipedia also writes down this normalization. And then Wikipedia uses the following very important expression, which tells us that the sinc function, which is this function here on the right, the sine of pi x over pi x, can be written as an infinite product of zeros, basically. So these are polynomials of second degree, and we have an infinite product of them. So it is quite intuitive because if you think about it, the zeros that we have on the left are the same as the zeros that we have on the right. If you check, this function here has the same zeros as the function on the left. And it's quite intuitive to conclude, without any mathematical rigor, that the two functions are the same. But I will not go through this in this lecture. And then, once you take this into account, you can use this formula to rewrite this infinite product over here. So you can write down the propagator in the very simple fashion that you see here. It's a very simple way to express the propagator. And once you do that, you can also replace the action S sub c, which is the classical action. We have an expression for that because we can carry out the integrals here with the expression that we saw at the beginning of this video, this expression here that I am highlighting. And then once we do this, we can write this expression you can see here, and then we see another expression written by Wikipedia. This is a summation over n from 0 to infinity of this exponential of minus I en t over h bar, where t is the difference between the final instant and the initial instant of time. And then we have psi sub n, which are some we have these two functions which are wave functions. And why does Wikipedia write down this expression? Now let me explain this conceptually. The propagator can be written as k, xf, tf, then we have xi, ti. This is equal to, we have some vector xf. You can think of this as a state, or you can also think of this as a vector. We are using the bracket notation. Then here we have e to the minus I, the Hamiltonian operator divided by h bar, and then we have tf minus ti, which if you want to, you can call it t, capital T, and then you have the state xi. Now at this point we can use the so-called completeness relations. In quantum mechanics they are really used very often, and here I will put a summation. So let me put the summation like this without specifying the integers over which we are summing. I will explain them in a moment, but we will have to carry out some summation here. Then we have xf, then I'm introducing some functions psi sub n, so we will have to sum over n, as you can imagine, and then you have psi sub n. If you sum over n and you only consider this, you will get the identity matrix, the identity operator. Then we have e to the minus I Hamiltonian divided by h bar capital T, and I'm going to put psi sub m, so we have a different integer here, so we also have to sum over this. We are introducing another completeness relation, psi sub m, and then finally we have xi. Now we can call this, in the Schrödinger way of expressing quantum mechanics, this is just a wave function psi sub n of xf star, whereas this one here is psi sub m of xi. And finally, you can see that what we have here, now I'm assuming that this wave function is an eigenstate for the Hamiltonian, so when this operator acts on this state, will give rise to e to the minus I, the energy with the subscript m, t, divided by h bar, and then we get the state psi sub m. Now when you consider psi sub n inner product psi sub m, you will get the Kronecker delta. So psi sub n, psi sub m, and you can do this because you can factor out this, because we have replaced the operator h with the eigenvalue, and this will give us delta nm if these functions are properly normalized. So once you do that, what you get is exactly the expression that Wikipedia writes here. It's very simple. And then Wikipedia uses the following identities, which I'm not going to explain because they come from Euler formula. They are quite simple to prove, these two, and in principle you can replace them in the expression that we have for the propagator. And you can rewrite the expression that we have here in such a way that you can see here. Now, conceptually, you can factor all these terms except for this one, e to the minus I omega t over 2, inside, so they are factored into this, they are contained inside this function r of t, which is just a definition. And in principle, you can also expand this function r of t in powers of e to the minus I omega t, because you can see that this function depends on e to the I omega t, or powers of that. And therefore, you will have a certain summation of terms of the kind e to the minus I omega t, they are raised to some power, right? So when we raise this to a certain power n, we have the integer n that appears here, and you are summing some coefficients c sub n over n, and you have such terms. And all those terms multiply this term here, e to the minus I omega t over 2. And you can see that Wikipedia really considers that. So we have e to the minus I omega t over 2 times e to the minus I, the generic term, n omega t, which you can rewrite like this for n equal to 0, 1, 2, and so on. And this term, if you think about it, should be equal to this exponential here that we have written in the other way by expanding this expression for the propagator that I showed you a few moments ago. This expression here can be written by using this summation with the exponential, and then we have these wave functions. And this exponential should be the same as this exponential here. So if you compare the arguments of the two exponentials, what you get is this identity, E sub n equal to n plus 1 half h bar omega, which is the expression for the energy spectrum of the quantum harmonic oscillator.